Yep, it looks like we're back. Great. So I said I would start today answering questions about shell programming. This is practically the lecture where we stop doing shell programming and we jump into other aspects. So let's see if you have anything related to the material. Let me know. I'll stay a few seconds. All right, so I guess no questions. If there are questions, though, please ask on Piazza. We'll monitor and reply. So today's material is the beginning of talking about processes and C programming and so on. What we have been doing until now for the first 3 weeks was pretty much to bring all of you up to speed with how to use Linux and get uh, introduced to shell programming and sort of get proficient with the command line, which is not something you necessarily have done much until today. We have chosen Linux versus Windows because it feels to be a little easier to use for teaching. And also, it's a good thing to get exposed to it since it's not necessarily as popular as an operating system. However, once you get further and further in this career, you will meet Linux more and more. So today we're going to stop with the shell programming. We will still use it, but it's not going to be the focus. And we will head towards basically changing the way you think things work. Until now, most likely you have written, most of you, short programs that were sequential. It started from first line and it went to the last line, and that was it. There was no question about the resources that program was using, no questions about how it interacted with other programs on the same operating systems, what side effects those could create, and so on. So this is where we're going today. So before actually starting on this, I just want to settle a few notions, which are actually quite simple. A program is a file on the disk. So it may be a binary that you compiled from C or whatever other language, or it may be a script like a shell script or a Python script. When such a program is executed, it becomes a process. So binary like a compile C program, when you run it, it becomes a process. A shell script, it becomes a process sort of through the interpreter, which is bash. So when you run a shell script, the process that you'll see is actually bash, which is interpreting that script. Same goes for Python. The process running a Python script will be Python. Now, a program can be run multiple times. You have seen this on your student server. Many people logged in, many people running VI. The program is the same, but it's executed multiple times. So practically a program can yield multiple processes. And processes that run simultaneously are said to be concurrent. This is the term that we will be playing with a lot. And this is where we are going. How can we create processes and how can we have them collaborate without corrupting the final results? So programs, processes, and multiple processes at the same time, concurrent processes. So one question would be, all right, let's see what processes do we have on the system. Now this is my local Windows subsystem Linux, right? And there won't be so much, but PS shows me the processes in this session. It will show me different processes in this session. You can notice that every process has a PID, a process ID, right? And here they have different processes IDs. Basically, I have here the bash that's interpreting my commands, and the ps command that I have just executed. Same goes here, but the bash is different. Now, if I want to see all the processes in the system, I can say ps-e, and it will show me everything in the system. Now, this being a local subsystem, it has very little stuff. If you do it on the student server or on a virtual box installation, you'll see there is a lot more going on there. But even so, you can see here the two bashes that I have, right? You can see the SSH connections. Let's do ps-e-f, which will also show us details about the processes and who owns them, right? So this is the owner, root. Root has only 3 processes here. Normally it would have a lot more. And then this is me. And I have an SSH client and the bash and another SSH client and a bash and then an SSH server for that client and another one here. The main SSH daemon, init, the first process in the system. So these are all processes, and you can see SSHD already is one program but has 4 instances, basically processes, and bash has 2. Now, another question would be, okay, so you can have many processes. How many? Well, lots, tens of thousands, limited pretty much by 16 bits, so that's 65,000. These are my Windows processes, right? And you see there is a whole lot of them. However, if I am going to see here the qualities of my setup, I have a nice voice. Thank you. I could actually be telling stories, and that would be not so useful, but more relaxing, right? Okay. So let's see this. Uh, so I have how many processes? 114, right? 114 processes. And then if you look here, I have 4 cores, basically 8 logical processors. Okay. So how come I can run 100 processes on 8 logical processors? What's the deal here? How can you have so many processes on much less processors? Oh, it's not 8 processors, but it is just a laptop. It's not that great. There are much better things. But as a laptop, it's decent. So how come I can run so many processes on so few processors? And this question would be maybe more obvious if you go back 20 years when there were no cores. There were just processors and there was one processor per system, and you still had tens of thousands of processes. So how can these things run simultaneously when there is only one thing executing them? So the response is actually quite simple. The operating system, which is underneath the whole thing, decides which process gets how much time on the processor. So, and it just gives time slices to every single process. And these time slices are like microseconds. So if you look at my screen, at least, I mean, the visible stuff is OBS, Word, and 2 PuTTY instances, right? So they all seem to be running at the same time. However, that's not true. The operating system gives a few microseconds to Word, then a few microseconds to PuTTY, then another one to OBS. So you could see things actually moving in both places, right? If I can do this here, right? Well, I got an error. It has to be a while. And instead of echo 1, I'll just show the date. So I can do this. Oh, God. Hold on. Right? So this keeps moving and then it keeps moving. They both have to execute at the same time, but it's not really true. Each of them does a little quanta of time, and those quantas are so small and they change so fast that apparently it's all happening simultaneously. But in truth, it's all discrete. All right? So this is how things work. Yes, the threads are actually we're talking about hardware threads. So now that you understand that you can have many processes and much less processors, I'll call them maybe CPUs to be easier to differentiate. So you can have many processes running on much less CPUs using this time slices. We need to ask ourselves, okay, what happens if you have so many processes, can they interact each other? Can they cause trouble to each other? And I will just say that when you have multiple processes that touch the same common resource and they don't really have proper rules for interacting on the same resource, we call that a race condition. So it's one of the issues that you will be bumping into. This class is concerned with ugly programming problems. You have memory problems for which you have Valgrind to help, which is great. But otherwise, memory problems are things that don't show all the time. They are fine at home, and when you come and present your problem, your solution, it will crash because that's how memory problems work. Now, race conditions are just the same, except that they are worse. You have no Valgrind to detect them, and uh, it's really hard to replicate them. But they do show. They do show. Yeah, deadlock will follow, but a little later. Same for mutexes. So race conditions do show much better when you have enough crowd. You know, you have enough load. When there is a lot of things happening at the same time and the crowd is bigger, then race conditions will start showing. But this is not always possible to do. So for now, what we're concerned with are two things. How do we create processes and how do we make them collaborate nicely? But for now, I just want to show you a race condition, and I'll start with a small shell script to see the effects of it, and then we'll move on to see how we create multiple processes and so on. So let's start with this little script. I'll call it inc from increment, and I'm just going to copy paste it from the notes. As I mentioned before, please pay attention because the quotes and apostrophes in these notes are not always exactly what I want them to be. So what does this do? Basically, it takes an argument, which will be a file, and then for 200 times, it reads what's in that file into K, it increments it, and it writes it back in the file. And then it increments n so that we do this only 200 times. Now, I've done this 2 hours ago for the Romanian section, and 200 is quite a lot of time, and I'm just going to make it at 100 so that we look at the screen less. Okay, let's give it execution permissions. What? Yeah, sorry about that. And now let's run it. inc.sh. And I have to give it a file. Let's call that file 1.txt. It doesn't exist initially, but then it will be created. And all right, it's done. And if we look what's inside, it's 100. So practically this script read and incremented and wrote and then read and incremented and wrote the value in the file until it reached 100. Now the question is what happens if we run several of this simultaneously? So let's make a script. We'll call it run.sh. And we copy this thing from here. And now you're going to get to see something that I haven't presented yet. So what does this script do? This script puts a 0 in the file, a.txt, right? In this case. Actually, not a.txt. Fine, we'll work with a.txt. We had 1.txt before. And then, so it resets it to 0. And then it runs 3 scripts, but this character at the end of the line says run script in background. So practically you get control over the command line, and then you run another one and another one. So you have 3 of these running simultaneously. So let's execute this. chmod 700 on run, and we run it. Okay, so now we check the processes. We have a lot of inks there going on. They're done. Let's see what's in a.txt. 100. So this is wrong. It should be 300 because we had 3 things. All right, I'll get back to your question about chmod. So we have 3 things that keep reading, incrementing, and writing. So practically we do 300 increments. However, the result is still 100. So this shows you how programs collaborating on the same resources can reach bad results. We can try this with more than 3. Let's do 10. 5, 6, 7, 8, 9, 10. Let's see what this does. All right. Yes. Okay. We wait for now. Remember these defuncts. I'll talk to them later on. Any minute now, they should be over. Okay, they are over. Cat a.txt. Holy moly. Now the file has the result 8. So what could have happened here? Why, instead of having 1,000, we have 8? So while you think of that, I'm just going to answer your colleague. Yes, chmod plus x is another way of giving permissions. I'm just very used to the 700, but you can actually read the manual for chmod, and you can say stuff like chmod g plus x, which means add to the group the execution permissions, or remove it from the group or from the others. You have the syntax as well. I'm just very used to 700. Okay, so what does the end at the end of the command line mean? Means run the program in the background. So practically we run multiple programs that run simultaneously. If we don't put this, then we will wait until this is ready, and only then this will be executed. This at the end of the line just puts it in the background, and you practically run them at the same time. Thank you for answering this as well. Okay, so black magic, it's not really black magic, or if it is black magic, then you will become sorceress, able to manipulate black magic. But what you have noticed here are two things. One program alone may work fine, but multiple may yield bad results. Further on, those results are not always the same, so they are wrong in many ways. Okay, we have an explanation here. If a program read the whole file and did all the 100 steps, then the next program would actually have to start from 101. I'm answering his answer here, right? My belief is that you have the 10 programs and they all read 0, right? And then they increment and then they all write 0, and so on. But one of these 10 programs manages to read the file after it was created by another. So his last step is actually incremented from 7 to 8, and then it writes 7 to 8, and you end up with 8. So it's really a mess, and we are going to learn how to create this mess and then how to order it. The point is, sharing the same resource is problematic. It's just like you guys trying, all of you at the same time, to bake a cake. It will be a disaster unless you're organized. So what we're doing here is just wrong, but you need to see this wrong, because until now most of you have written sequential programs that were just fine by themselves. Well, this is me showing you it's more than that. You have to take into consideration interactions with other programs. So let's try this in C. Uh, yes, all at once. So just to clarify on the code, what I believe happens, uh, you may have only 2 instances of this. Let's think 2 instances of this, and each of them reads the file, and the file, let's say, has 7 in it, right? So both of them will have k equal to 7. They increment k to 8. They both write 8 in the file. So although we had 2 increments, the result is 8 because we have this unfortunate correlation of instruction order, and the final result is wrong. And this is actually quite common, and it becomes quite frequent if you have a lot of executions done simultaneously. Now let me see what you guys are saying. Okay, Yeah, the cake is a lie. I don't know what portal pog means. I was experienced. Okay, so if you're thinking about the university site, um, what you have on the university site is mostly read. So you can all read the same screen just like you do now. You can all read this screen fine, and there is no problem. But if we were all streaming at the same time, it would be a mess. We wouldn't know what we see from whom. Now, if you log into the university site, like I do, to upload grades there, and somehow somebody else logs in with the same account as me, and we both upload grades, then yes, that would lead to something very weird, and grades would be corrupted. So indeed, it's about modifying a common thing. But sometimes it's also about reading something that is being modified, and then you get partial things, incomplete reads, or inconsistent reads. Okay, you might get a piece of the old value with and a piece of the new. All right, let's do this in C now. I'm just gonna copy this program from here. It's the exact same idea but done in C. Now C will be much faster than shell because instead of running a command for every operation of read, increment, and write, we will only have instructions which are extremely fast. But the value will still be corrupted if we have enough of a crowd. For instance, we will have 255 times, so it's 65,000. Okay, so let's see what do we do here. We open a file, right? The file is given in the command line. And if we get a second argument named reset, we simply put a 0 in that file, but we work binary. So this file will contain 4 bytes, which will be an int. All right, so let's say we are going to work with a file named b, and because the way I'm opening it, I'm actually expecting the file to exist already. So let's say touch b. This created a file b which has size 0. Now let's compile the program. Yeah, I think I forgot to save. Let's save. Now it should be happier. All right. So if we say inc b reset, now we have b and it has a size of 4. And if we look inside it, we see that it contains an int with value 0. All right, so we initialize it. Now, what do we do? Without reset, we will cycle 65,000 times, and we do what? After we open the file, we position at the beginning of the file, then we read the int, we increment it, we position ourselves again at the beginning of the file, and we write the int. That's all we do. Read an int, increment, write an int, and we keep repositioning with lseek. Then we close the file. So basically, after running this program just by itself, it should the file should contain 65,000 something, and if you check, this is actually 65,000, 65,025. Now, the same issue if we run this multiple times. Let's write another script. Let's copy the run sh into run csh. All right, so instead of this, we will have inc b reset. And then inc b. Right, and then we run this just like before I think it's 11 times now, right? So this should have a really large value, but we'll see what it does. So run C. All right, we ran it. Now this is, it will take a while. We see this ink still running. It is quite slow probably because it's a subsystem, but that is actually good for us because slow allows us to see these problems. Fast will make them quite invisible. So XXD on B now has this value. We don't know if this is actually 650,000 or more, but if we run it again, and I'm not going to run it here, I will run it here so that we keep the other result displayed. We should end up with another value. Let's just wait for a little bit. Should be done soon. And then we'll see the result. All right, it's done. XXDB, totally different value. So what you notice here is the inconsistency of the final results of running things concurrently without any control. All right, so this is a race condition, and if there is not much of a crowd, they will happen every now and then. You write a piece of software, you sell it, and then your client comes and says, you know what, everything was wrong. And then you check it, and everything works fine. You cannot reproduce the error. This is the biggest issue. You cannot reproduce it. So how do you fix it if you cannot reproduce it? Pretty much the best defense against this is knowing what you're doing and your logic. Make sure things are done right. So I'm going to show you now first how can you create such concurrency in C, and then how to control it and so on. So let's move on to the next section, which is about how do you create processes in C. So here we're just going to talk about an API, which is specific to Linux, and it's fairly strange. It's an old API, but it does the job and it's still used today. So here we go. We're going to enter an area where we're going to talk about parents and children and zombies and death, basically. You'll see how this weaves together. So the way you create a program, a new process in Unix, is using the system called fork. This is a function. And this will actually make things very weird because up until today you wrote a program that ran from the beginning to the end and it was just a process. But now we're going to write a program that will at a point become two processes or more depending on the situation. So let's have a look at this. Let's create this C program and see how fork works. Okay, let's write. Now I showed you already, I just want to make a short parenthesis. I showed you already how every process has a process ID. And if I display details, it also has a parent process ID. Okay, so keep this in mind. These are just numbers, and they are unique among the executing processes. So let's compile this. All right, you see this? This is what happens when you copy paste from Word. These are the wrong quotes, and because of that, it doesn't compile. They look really nice typographically, but not very nice for programming purposes. So let's compile again. All right, now it's happy. So what does this code do? It prints before, then it does a fork, and then it prints after. So let's just run it. And what you can see is that it prints after twice, although the program only prints after once. So how come this became this? So I'm going to improve a little bit the program to show a bit more. So let's display the ID of the process printing and the ID of its parent. So getPID is a function that gives me the process ID of the current process, and pPID is it's the parent ID. All right. So let's compile and run again. And let's do a PS. So what are we seeing here? We're seeing the first process, which prints before, just before fork, right? And it has ID 16058, and it's child of 261. 261 is actually this bash, all right? And if we look at all the processes in the system, you'll see that bash is actually a child of an SSH, which is a child of another SSH and another, and eventually it's child of process 1. Okay, now after the fork, we have two processes. The initial process prints after itself again, but then the child process that it created also prints after. And you can see that this is the child ID, and you see that it's a son of the previous process. So now you need to really visualize that this function is weird. Once you run it, you have two copies of your code running. It's not just one copy, it's two. All right? And every copy continues from where it left. So practically, they continue from here. So let's look at the code here. Okay, let's put it in a file. And please try to figure out how many processes it will create. I believe the answer is unfortunately written there because that's how it works with nodes. But try to understand why. So what we do in this code is really simple. We have a for from 0 to 3 and we call fork, and that's it. So let me, whoops, that's not what I wanted. No, it's not. Well, you're thinking when you say for, right here, when you say for processes, you're thinking parent plus 3 more processes, right? But you are forgetting that every process continues from where it was left. So let me improve this code, okay, by adding some printfs. First, let me compile it, just to make sure I don't have any weird quotes. All right, this is good. It becomes like a tree. It actually, what you're seeing here is exponential multiplication, somewhat very actual nowadays with this virus spreading like crazy. So let's put a printf here. So it will be printf, and it will be the PID and the parent PID, right? All right, and then we'll print this here as well. We'll put here a -1. You'll see why. And then here we'll print, oh, we'll print the value of I as well. All right, so let me read the comments. Yeah, in a way, the virus, well, that's what the virus does. It actually forks a lot. It gets in a cell and it tricks the cell into producing more viri. That's what it does. And then because it's so easy to pass from one to another, we become hosts and then we multiply it. And yeah, okay, so wild fork, we're gonna talk about this in a minute. This is what you can call a fork bomb. Yeah, biology class, it's ancestry class, it's gonna be weird. Genealogy, operating system touches all this. All right, so let's compile this and let's run it. and then see what happens. So initially, the initial process prints a -1. Oh, darn, hold on. Forgot to put a space here. Not good. Okay, so let's clear, recompile, and run. Okay, so initial process prints this -1, right? And you can see that it's child of 261. And then, yeah, don't run this. Don't run it unless you want to bring your system to its knees. So then the first process, the parent, runs fork, and suddenly you have two processes printing for I equals 0. You have the initial process and then the child that it created. And then they both continue with the code from where it was left. So they cycle back and do for value I equals 1, meaning that the two initial processes, this actually, these two, yes, these two create each one of them another child process. So all four will write. And then because I is only 1, all four of them cycle again, and then they run, each of them fork, 4 more children, and then you have actually 8 processes printing out. Hence, with not counting the parent process, 7 were created. Let me see questions. Okay, well, don't expect it to actually explode. Although, if you try hard enough, that may happen. Uh, there are limits that are imposed to regular users. For instance, on the exam machine, after being locked up by a student who wrote a fork bomb by mistake, and actually he was very insistent and canceled about 4 exams, I put a limit, so you can only create at most 30 processes, so the system doesn't go down. I mean, it simply not. It doesn't go down. It's just you can't really create more processes anymore, so nobody can work, right? So I put a limit, and then we are all okay. All right, so what you see here is how this fork actually multiplies exponentially. But then, so the way to visualize this is whatever this code does, you see it's really simple. It's going to be executed in multiple copies. So the next question that comes up is, well, this is interesting. Yeah, fine. You can run fork and you make a copy of the program and then they both continue from where there was left. But what's the point? Why would I create an identical copy of my program? It would make sense to create copies that each does something else, right? Why would I create several processes to run simultaneously unless I do it to use the resources that I have, meaning multiple processes, multiple cores? Okay, but then even so, if those things do the same thing, it's pointless. So there has to be a way to differentiate between these processes to know this is the parent and this is the child. So how do we do that? So to do so, let's look at this piece of code here. See if I can convince it. Yeah, mostly. So what this code does is actually quite simple. It runs fork, but it also records the value that it returns, right? Fork and then a print. Yes, fork creates a process that does what the original program was going to do, but the original program also does the same thing. It's like you get cloned, right? While eating Cheerios, you get cloned, and then you have two of you continuing to eat Cheerios. Although the Cheerios will be not cloned, so then you're going to have a contention, a race condition on the Cheerios bowl. It kind of goes this analogy. So let's look at this code. Practically, we run fork and we print. Ignore the wait. The wait will be explained later. But what we do is we record the value returned by fork, all right, and we print it out. So let's see what happens. This program will print two lines. One will be printed by the parent, one will be printed by the child. And you can see that this is the child because it has as parent this guy. Now, the interesting piece is R. Fork in the parent, R is 1613, which is exactly the PID of the child. Okay? In the child, R is 0. So basically, fork returns in the parent the PID of the child, and it returns 0 in the child. Now, this is usually hard to grasp initially, but your code past this point becomes 2. You have 2 processes. It just cloned. So now each of them continues execution. However, fork helps you know where you are by returning the PID of the child in the parent and 0 in the child. This is really easy to remember if you think of this like this. The child knows its PID and knows its parent PID, but the parent needs to know the child PID. So then fork gives the child PID to the parent and nothing to the child because the child already has that information. All right? Ignoring the wait, I'm going to scroll down and show you the standard way in which you will write fork this semester. You can do many things, but this is the safest way. So what we do here is we actually differentiate between code executed by a process and by another. So we run fork, we record its return value, and if that value is 0, we do something. This code is executed exclusively by the child. Why? Because after this point, you have two processes. Both of them will evaluate the if, but the parent will get the PID of the child. So, and that will not be 0. So the parent doesn't go into this if. The parent skips and comes here. The child goes in here. And then we put this exit. If we don't put this exit, then the child continues with this code as well. And then it's not a very clear separation between child and parent code. So I insist we put exit 0 here, always, at least for this class. And when you know how to do things better, then you'll make your choices. But for this class, stay safe. Put an exit here. Why? Why exit? Why not return? In this case, you could also do return, and it's fine because you're in the main function. But if we were doing this in a sub-function, then then return would only get out of that. And what we actually want is to exit the entire process. So this is code executed only by the child, and then we make sure that the rest is only for the parent and there is no mix-up. Okay? So this is how you will write your forks. Now, talking about the fork bomb. Fork bomb is what a colleague of yours wrote. I'm going to write it in C here, right? And it kind of looks like this. So if you do this, this is simply going to multiply itself. At every step, it doubles. So in about 16 steps, stream is gonna close soon. What does that mean? Twitch is imposing a limit or something? All right, that's not good. But if soon is 5 minutes, then I should be done in 5 minutes. Oh, all right. Sorry about that. Didn't see the joke. Uh, so in about 16 steps, this piece of code will yield 65,000 processes. Each of them will, keep trying to create child processes. but you're limited to the number of processes you can have. And there are many limits, but let's say the uppermost limit is the number of PIDs that you can have, how many process IDs you can get. And it's pretty much 65,000. So in 16 steps, you cannot create any more processes. You cannot SSH into your machine, nothing, because there is no way to create a new process. They're all taken. Obviously, fork will, I mean, those thousands of processes will keep cycle and run fork, but fork will fail, will return a -1 or something. So then what do? You can try to kill some processes, and let me show you how that's done. Basically, you can check the IDs of the processes. You can see the VI here has ID 16 something. So you can just say kill that ID, and it kills it dead. All right. So you can try to do this. Okay, kill -9, somebody shows. Kill -9 is the ultimate killer. We'll talk about it next time. But if you do this, what you're going to kill one process of 60,000. And as soon as you killed it, one of those thousands of cycling forks will create another one. So practically, it's really hard to get out of one of this, but what you can use is pkill, which actually kills all the processes follow some pattern. So you can kill them by the name and it will kill them all, and then you're out of it. If you try one by one, there will always be another fork succeeding and filling in the empty slot. All right, so I think it's time. I mean, there is more to say here, but we'll do it next time. I think it's time to talk about wait and zombies and whatnot. So let me, yeah, you have to be fast indeed. So let me scroll back. There was a point here where I showed you defunct processes, and I told you to keep them in mind, like this. So let me tell you the story of wait and zombies. In short, and this will sound really weird and cruel, in operating system, parent processes have to wait for the children to die, for the child processes to die, or else they become zombies. And zombies are bad, not as they are in movies, but still bad. So what's the story here? Uh, if a parent process creates a child process, it does it for a purpose, to do some calculations, to perform some operations, right? Now, it's only normal that the parent process is interested in the execution status of the child. At least is interested in the exit code. Did it exit with success or with failure? So this is actually quite hardwired in the system. And if a child process stops, finishes execution, the system holds it in a state of zombie, meaning it doesn't execute anything anymore, so it's dead in a way, but it still exists in the table of processes occupying a process ID. And it holds it there until the parent says, let me know how this finished. Give me the exit code. And that the parent process does with the command wait, with the system call wait, right? As soon as the parent calls wait on a child, the child gets out of zombie and disappears. All right? So the child is a zombie from the moment it finishes execution until the parent calls wait. Now, wait should get here. Yeah, I know. This is bad. Sorry about it. Don't show this at home. People will think we're weird, which we are in a way, but not in a bad way. So wait gets a parameter here, all right? This is supposed to be a pointer to an int in which you would get the exit code of the child process. But we don't really care for that in this class. What we do doesn't require, so we just pass a zero or a null, right? Wait pretty much sits and does nothing until one child finishes and then moves on. If you want to wait for a specific child, then you have wait PID. It's another function that you can call. But this is going to be good enough. We just need to call enough waits to match the number of children that we have created. All right. So about this zombie thing. So child process is zombie between the moment it finishes execution and the child calls wait. And then wait gets the exit code. There is no point to keep the child in a zombie state, and the system clears it out. However, there are situations where the parent finishes execution before the child, which is not really great and not supposed to happen, but it does happen. So let me scroll up and you'll see a case like that, I think. No, down. Let's see. I think it showed up at the point. So here. So what we've done here is we ran all those forks, but look at this. At the point the parent of this children processes became process one, whereas it should have been one of these. So what's the story here? So you go back many years, the system had a real problem with the zombies. If anybody on the system had an error in a program and left a zombie behind, meaning the parent finished execution, forgot to call wait, the zombie would be stuck there. And over time, you'd get a bunch of zombie processes, and you'd need to reboot the system to get rid of them. But then the solution to this situation, because you cannot avoid it, you'll have users that run programs that crash, and then you'll end up having zombies left behind. So the solution to this was that if the system detects that the parent dies before calling wait, or you find the child process in a zombie state and the parent is not there anymore, the system automatically moves the child as child of process one, which is init, the first process in the system. And then process one automatically calls wait, and then the zombie is cleared of the system. So that's why you sometimes see that a child actually processes child of one, which is strange because one is something else. That's what happened. The parent of this, the actual parent of this process ended before the process, so it was automatically moved to be child of process one. Yeah, or maybe, nah, it's more like an adoption. But then you go bad because they adopt the child, which is a zombie, only to kill it, right? So we can go really ugly here, but we're not gonna. So I think this is where I'm going to stop today. Um, I just want you to focus a little bit and get the idea that a simple program like this actually splits into executions, which is not something that you had today. And you actually kind of have to split your mind when you write your program. You have to split your mind and you look at it and you say, oh, so this is going to be run in another process simultaneously with this. You have to be able to do this. All right. So I'm not sure what you guys are talking with this there, but I'm not going to go into that. Oh man, this is no, we're not going to do that. It's just processes, all right? So next time we will look a little bit at zombie processes in a more complex scenario and signals. But for now, I think I passed on to you what I needed. I want you, let me start Chrome. and check the class web page. So we are somewhere here now, right? We're right here. And supposedly next week is gonna be the last one when I teach from my couch and you watch from your couch. But I wouldn't bet on it. It's probably gonna extend. So we don't know yet what we do about these tests. I'm trying to figure out a way of doing them remotely so that we don't have something piling up all the way to the end of the semester. And what I want you to do in the meanwhile is to exercise grep and Unix shell. Also go through all the examples here, implement them, run them. Not this one. So for this is mostly like a pseudocode thing. But I haven't taught this yet. But the rest of them, run them, execute them, learn how they work, deal with with compiling issues, get through the whole thing. I keep repeating this. The best way to learn this stuff is exercising, and obviously, you're not going to be able to do it right from the beginning. But what you should do is look over this solution, try to understand everything that's here, then put it aside, don't look at it, and try to do it yourself. And if you fail, come back, look at it, then put it aside and try to do it yourself. So it's crucial that you don't really copy from here there, not nor keep looking, but rather try to understand, put it aside, and try to reproduce. Understand and then reproduce, and this will actually uh, get get into your memory and into your reflexes, and you'll get good at it. I, I've read this somewhere, and it seems to be a good system for learning. All right, so if there are questions, please type them in. I'm reading your comments. Oh, how do you paste into the terminal? Okay, that's a good question. Control Shift V. I never do Control Shift V. I just copy from here, okay, and then I right click here. That's it. I just right click. It's quite easy. You can also, if you're on a Linux terminal, watch out. So if you're not in Windows, you have to middle click. You have to click the wheel. You can actually configure PuTTY to do that from somewhere here or something. There is a place where you can configure how to do the paste, but it's better to leave it in the Windows style because you have other command lines which use the right click and then you get confused. All right, any other questions on this matters? It is working in VI as long as you are in insert mode. If you're not in insert mode, what you're basically going to do when you right click is you're going to send a bunch of commands to VI. As soon as it gets to an insertion, meaning A or I, it will start typing. So if I do VI, right, and then copy this, actually, let's try to copy this, right? And I come here and I paste, it actually did it. Sometimes it doesn't. It starts running typing. I mean inserting only after you reach a command that says insert. So make sure you're in insert mode. Okay, this lecture should be recorded. I think you should find it online for 2 weeks. I'll try to download it and then put it on YouTube. Some people say that I could do this on YouTube uh, as well, but I didn't know it had chat, and I need this chat to interact with you. But if it does, I'll consider that as well. But for now, I think Twitch worked fine for everybody. So unless you had troubles, but you didn't say anything. Yeah. So yeah, as long as I think we'll stay with Twitch. It's good enough, and it's funny too. All right, guys. So that's about it. Enjoy the rest of the day. Stay safe. Stay at home. Don't go out. It's better to stay at home than in the hospital. See you. Bye bye.